tomorrow, or you can just have it as one of your job visits. You can do it.
Okay. When tomorrow would you be able to?
Just about any time?
office hours?
Yeah, so 8:30 to 9:30 in the morning, or anytime 1 to 5.
Okay. I think I might do it as a drive to work because we leave on that.
That's fine.
We're getting into the whole fire mystery stuff.
All right. So does everyone have their calculator out and ready? We're going to be doing lots of calculations today. So if you don't have it out, go ahead and take a second to find it. All right, so just as a reminder, we have mastering tonight. Then your next mastering is not due till the Monday after spring break. So, but you already know enough information. If you want to work on it over spring break, you can totally do it. Because you have nothing else to do over spring break. Like me, I'll just be hanging out here, grading masterings. There is a chemistry seminar tomorrow at 11 a.m. If you attended the biology one yesterday, don't forget to send me your summary. I've gotten quite a few of them. And then we'll do an individual quiz Friday. If you're not going to be here Friday, not a big deal. There's some options. So just come see me about that. All right, so let's continue using our Henderson-Hasselbalch equation, putting it into practice, and then we'll do some other examples. All right, so let's calculate the pH of a 1 liter solution that contains 0.05 molar acetic acid and 0.075 molar sodium acetate. The Ka of acetic acid is 1.8 times 10 to the negative fifth. So, as a reminder, our Henderson-Hasselbalch equation is this one. My marker just died. I'll throw that away. Alright, so it's pH equals pKa plus the log concentration of base over concentration of acid. So, do we know the concentrations for over here? Were they given in the problem, these two concentrations? Yes. Were we given the pKa? No. How do we get the pKa from what we were given? Okay. All right, so negative log 1.8, negative fifth. Everyone get something similar to that? Okay. So now we can plug in all the other information that was given to us. Let's go ahead and take a second and figure out what the pH of that solution is. Everybody get something in that ballpark? Yes, good, good. All right. So let's go ahead and do some more problems that involve using the Henderson-Hasselbalch equation. And we'll talk about what cases it works and what cases it doesn't work, and how we know when to use it. All right, so preparing a buffer solution. For a buffer to be useful, it has to have the following two characteristics. You can't see them. This is number one. This is number two. First thing is that, right, the point of a buffer is to be able to control the pH of a solution. So when I add a little bit of acid to it, the pH doesn't change. If I add a little bit of base to it, the pH doesn't really change. So its job is to be able to control the pH at a desired value. All right, so using our same equation, we can kind of think through how that works. So in the previous example, right, we had acetic acid and sodium acetate, and we found the pKa to be 4.75-ish, and our final pH was 4.9, right? They are close in value. And we talked about this on Monday. What happens if these molar concentrations are the same? What's the value in the parentheses? And then what would be the log of that? So if I have equal molar concentrations, the pH is the pKa. So if we know the pH we want, you want to choose an acid. Has a pKa value close to desired pH. Alright, so if I know what pH I want, if I want pH, in the previous case, 4.7, well then I did a great job of picking acetic acid because its pKa is real close to 4.7. Which means I can then, if I make those equal, then exactly the pH I want. If the pH I want is a little bit different, like if I want a pH 5, but that's 4.7, well then I just adjust the ratio of base to acid to get to the pH I want. So the key is going to be know what pH you want, find an acid that has a similar pKa. And then the buffer should also have the capacity to control the pH depending on what you're adding to it, which is kind of the definition of a buffer. Bless you.
Thank you.
And the way we're going to do this is to choose a good conjugate acid-base pair. So let's work through a mathematical example that kind of looks at these 2 points and hopefully proves them to you mathematically. So let's take a look at this. I know I need a buffer of pH 2.5. Which of the following can be used to make a buffer? And then, so that's question 1. Then question 2, what ratio of conjugate acid base do I need to use to get to the pH I want? So, let's take a second, look at those 3 choices. Think to yourself, what is required for a buffer? Right? We need a conjugate acid base pair. Are all 3 of those conjugate acid base pairs? Alright, we'll start bottom up. So is H3PO4 one of our strong acid bases that you know? Yes, it's phosphoric acid. It should be one of the strong 6 you know, phosphoric acid. So if we know that's phosphoric acid, how many protons would it lose to make its conjugate base? That is a conjugate base, yes. Yeah, but those are always our spectators. They just hang out. So really, I would write this as H3PO4 and H2PO4 minus, and a sodium, which isn't interesting. It just kind of floats around. All right, what about acetic acid? Acetic acid loses a proton. Is this a proton-less version of acetic acid? Yes. So, right, I could rewrite this as Na plus and CH3CO2 minus. Right, so now I have, ignoring the sodium, I have an acid-base pair. Okay? Hydrochloric acid, is it one of our strong acid bases? Right, it's one of our strong acids. Which part of this, when we do hydrochloric acid, do we ever write it as H plus and Cl minus? Or do we write it more appropriately as a Bronsted-Lowry? Okay. So, right, we had these questions. We had this and NaOH, right? Something like that. So in this case, right, this is the acid, and it just gives off a proton. And that's okay to write like that. But it's more appropriate to write it like this. Something like that. All right, everyone's confused. Let's try this. I have HCl, right? If I combine that with water, what would be one of the two products made? Okay. And then what's the other one? Okay. So if this is acting like an acid, that's acting like a base. This is the acid, this is the base. If this is a strong acid, we're mostly going to make this, right? Does this actually have a conjugate base? Is this actually a base? Is chlorine minus? If I just told you chlorine minus, not a base, right? So this this is a conjugate acid-base pair, but I mean that's just water. Doesn't have a conjugate base, because chlorine minus, we would never consider that to be a base. What's the likelihood of this chlorine minus taking back the proton to remake the HCl? Right, pretty much 0. So, looking at our three options, we definitely have 2 conjugate acid-base pairs. This is not a conjugate pair. Man, we got the Wednesday doldrums. All right. You guys will get excited here in a little bit when we start doing some math, probably. Hopefully. Okay, so we've narrowed it down to 2 possible choices. All right, so this is a bad choice. Don't use that one. All right, let's take a look at then our 2 last choices, acetic acid or phosphoric acid. So I would look up the pKa's of these 2. And we just solved that. This was 4.74. And this, I'll look up on my table, has a pKa of 2.13. Of those 2 choices, the first choice or the second choice, what is the better choice to make a solution of pH 2.5? Second choice. So then let's do the second part. What ratio of acid to base do I need to make the pH I want. All right. So let's see here. So that's our buffer solution, right? We have the acid reacting with water to make its conjugate base and the hydroniums. If I wanted to write the K, in fact I do, I want to write the Ka expression for this reaction. What goes on the top, the products or the reactants? Okay. And I got two products. How many reactants do I put on the bottom? Just one, right? Well, I ignore that water. All right, and we know the pKa is 2.13. How would I find the Ka from the pKa? Anti-log. So 10 to the negative 2.13. All right, what other piece of information do I have that I can plug in here? So now I know this is 7.4 times 10 to the negative third equals. What other piece of information do I know about the solution? Or no, I want it. We know the pH, right? I want pH 2.5. How does that help me find any of these concentrations?
You find the concentration of A3.
Yeah, right. So if I know pH is 2.5, that must mean this concentration, we do the exact same thing. There we go. All right, so how do I get this ratio by itself? I just want the ratio. I'm sure everyone's working really hard at your own desk, so I'll just go ahead and do it over here, right? I divide that by this. So that should turn out to be 7.4, negative 3, divided by 3.16, negative 3. Now this ratio, so how much more of the base do I put in compared to the acid?
2.34 times.
Yep, so I want a little more than twice as much base than acid. And that makes sense, right? pKa is 2.13. If they were equal, if these were both 1, right, if the ratio was 1, that would be 2.13. Is 2.5 more basic or more acidic than 2.13? More basic, so what should you add more of? Base. So I'm saying add about 2 times as much base compared to acid to get to a more basic pH. Okay, some slight nods of agreement. Let's do some more problems then.
If you set that equal to the 2.34 is equal to H2PO4, that equation right there.
Mhm.
This one, you set that equal to the base, that wouldn't be twice as much acid. See, like,
I see what you're saying, but since it's a whole number, you're saying this should be 2.34 to 1, right? It's the same fraction as this,
okay.
so I want,
We're looking at just
yes,
base ratio.
yeah, the strictly the ratios, yeah. All right, so let's see here. What do I have as my next practice? Ooh, I think I have this next. All right, I want to change this question. I want to change this to I want to change that to find the pH of the buffer. All right, so this is going to be slightly like one level more. Oh yeah, Cody.
That 2.34, that's how much K is that, correct?
That'd be the ratio of the two.
Okay.
Yeah, so either in moles or in molarity of how much you add. All right, so let's say I have a solution that has 25 milliliters of 0.1 sodium hydroxide and 35 milliliters of acetic acid. I think that's what that is. All right, so first thing we always do is write our balanced chemical equation, right? All right, sodium hydroxide, strong acid, strong base. Strong base, right? Do I care about that sodium? No, totally don't care about it, so I'm just going to use it as this. So that's a strong acid. Is this one of your 6 strong acids or 6 strong bases? No. So it's a, if I know that's a strong base, what is this most likely then? Weak acid. So I have a strong base, weak acid. So then what is going to happen to this proton off the weak acid? Is it going to get one more or is it going to give it away? Give it away, right? So we have to make water. All right, so now this is where buffers get different than the other things we've done before. In every problem up to this point, I've added 2 things together to one volume. Right, I've said I've had 0.1 molar and 0.2 molar all in the same container. Now I have added 25 mils of this and 35 mils of that. So I have to look at the moles rather than the volume, like molarity. So what we need to do, step 2 here. All right, so we need to find the moles, the hydroxide, and moles of our weak acid. So if I know the volume and I know the molarity, how do I use those together to find moles? Multiply them together. Right, if I know the moles and I know the liters, I can just find moles that way. And I'll do the same for the weak acid. right, so we're ready for our first, not the other ice charts haven't been interesting. This is going to be an interesting ice chart. So, get myself a blank piece of paper. All right, so now we know the moles of all of the components, right? So in order to figure out the pH, I need to figure out the ratio of my conjugate base and acid, and I can look up the pKa. So if I know this ratio, which I can get from an ice chart, and I know the pKa, I can figure out the final pH. Okay? So let's go ahead. I'm going to cover up this just because I'm lazy. I don't want to rewrite the equation. But if you didn't plan out, because I didn't tell you to plan out, rewrite the equation so we can make our ice chart. All right, so initially, how many moles of the hydroxide did we find based on our moles? All right, 2.5 times 10 to the negative third. So we put that in there. How many initial moles of the weak acid did we find? That, 4.3. All right, that's water, which we don't care about. How many initial moles of the conjugate base did we have? 0. Okay. Now, I have 2 reactants and no products. Which one of my 2 reactants will be used up first? The hydroxides or my weak acid? How do we know if the hydroxides get used up first? 1 is the strongest and 2 is the limiting. So both are true. So the strong acid's going to definitely completely dissociate. And it's also the limiting reagent. So it will be used up first. So this change, which number do I subtract then? Do I subtract 2.5 or do I subtract 4.38? Subtract 2.5. Which then means I add that much over to the other side.
Just out of curiosity,
Mm-hmm.
why on the others have we subtracted or added X?
Because we didn't know X. We didn't know how much would get used up. The other cases, we've never had 2 reactants. We've always had like a reactant or a product or some kind of combination. This we have, from here on out, we're going to have a lot of 2 reactants make 1 product.
Okay, so we actually know the amount.
Mm-hmm. We'll know the amounts of just about everything going into our solution.
Okay.
Is that your question, Cody? No. Oh.
Why did we choose the hydroxide to subtract one?
1 is the limiting, and 2 is a strong base, which means it dissociates completely. So both are good reasons. All right, so how much hydroxide do I have left after it dissociates? 0. All right, let's do the subtraction and figure out how much of that we have, the weak acid. All right, so now what one last piece of information do we need to know in order to find the final pH? pKa. And since we've done acetic acid like 15 million times, pKa is still, I don't know why, like when I'm coming up with problems, I'm always like, oh, acetic acid. Oh, acetic acid. Oh, we'll do acetic acid again. I don't know why I have any good, yeah.
For the test and stuff like that or homework, will you give us the pKa or do we need to look at the table?
On the test, I'll definitely give you the pKa. I think in the homeworks they typically give you the pKa, If not, it's in one of those drop-down things that says tables and charts. So. All right, so now we can plug this in. And why can I do this ratio in moles instead of molarity? We talked about this one day. Right? The volumes cancel out. And so now I'm looking at the total volume, and the volume top and bottom will cancel out. So we can do it in moles or molarity. Both are good. So our base is over here at 2.5 times 10 to the negative third, and our acid is 1.88 times 10 to the negative third. All right, so let's figure out what the new pH is. I guess not new, BPH. Does that make sense from the mole ratio? Right, the mole ratio, we had more base than acid. So we would expect the pH to be a little more basic than the pKa. Right, shifts it to a higher number. Yeah.
In the ice charts, is it always going to be the conjugate pairs that still have, well, is it always going to be the, like, are they still going to have numbers at the end instead of doesn't drop that?
Yeah. If I'm going to make a buffer, I have to make it so that the conjugate acid-base pair are the ones that are still in the solution. Otherwise, there's no longer a buffer. That'd be a trick question. I want tricky. Yeah.
We always gonna use skid buffers, so like a way to check this would be to ensure that our pH is as close to our pKa.
Yes, I will not give you a buffer that has a terrible ratio.
Okay.
Yeah.
Cool.
Cody.
Why would you ask for this if they're completely associated? Like you said, we were using hydroxide because they're completely associated with everything. So if you didn't have that strong base or had that strong side, the reactant side would be used to.
Whichever one the limiting is.
Okay.
But typically these problems are set up so that I'll add a strong acid or a base to a buffer pair and figure out what the pH changes to. How about we do another one of those? Let's see. This one's in your PowerPoints, and I have like 4 or 5 more that we can do, depending on how confident we feel at the end of these. These problems, all they take is practice. I mean, right, we haven't actually thought about anything particularly challenging, right? pH, it's going to be an acid or base, conjugate pair. The hardest part of these problems is like reading them and trying to figure out what piece of information are they looking for. Every single time that you're going to write your balanced chemical equation, you're probably going to need an ice chart. And in this section, we're going to need stuff in moles rather than molarity. There's going to be some good guidelines. So let's say, I'm going to use acetic acid instead of acid again. Eventually, I'll come up with another fun pair of weak acid conjugate base, but it's just a go-to. All right, so I made a buffer solution by adding 4.95 grams of sodium acetate to 250 milliliters of 0.150 molarity acetic acid. I want to know what is the original pH of this solution. Yeah.
It says NaCH3CO2H.
Hmm.
There not be an H.
There should not be an H on the end. Just kidding. Good typo. All I have to do is copying and pasting incorrectly. All right. Yeah, so that should be the base and the acid. All right, which equation do we use to find the pH for a conjugate acid-base pair? Henderson-Hasselbalch. That's right, everybody. Good job. All right. So if we need the Henderson-Hasselbalch, we need the mole ratio of bases to acid. So we need to find moles of base. We need to find moles of the acid. So I gave you grams of base. And let's see here. Make sure I wrote it down correctly. 3, 12, 15, 16. Yep. So the molar weight of the base is 82. So go ahead and take a second, find the moles of base and acid, because now you have everything you need in order to find that. Everybody at ballpark pretty close to that. All right, so then go ahead and plug it into because we've used this pKa about 4 million times now, still 4.74. Based on the moles, would you expect it to be more basic or more acidic than the pKa? More basic, right? We have more moles of base, so we expect it to be more basic. So that's a good check to make sure that your pH that you calculate is correct, that you got the right top and bottom. All right, so that's question 1. That's the original pH of our solution. Question number 2. What is the new pH when I add 82 milligrams of sodium hydroxide to 100 milliliter aliquot of this solution? It's a lot of words, a lot of information in there. It's asking for an ice chart, right? It's saying I have a solution that I know the moles of each, and now I'm going to do something to the solution. What is the new mole chart? What is the new ice chart? New pH. So, I've been looking forward to this all day. I'm very excited. This is my favorite kind of ice chart. All right, so everybody have this part for, can I cover this a little bit up? Okay. Just means sample size. It's a snazzy word for saying some. Because scientists don't want other people to know what they're talking about, so we make up our own fancy lingo. That way, it sounds like we're talking gibberish. All right, so for part 2, first thing we need to do is find moles of my sodium hydroxide, right? It's got to be in the moles, because we have moles of conjugate acid base. Molar weight of NaOH is 40.0 grams per mole. And you have 82 milligrams of that. Give you guys a second to calculate that out. Can we get something like that? Good, good. All right, step 2. Let's write out our balanced chemical equation. All right, so I know sodium hydroxide is going to be one of the reactants because I'm adding it to the solution. All right, so if I'm adding it to the solution, it must be a reactant. So I have this. What is the other reactant going to be? The sodium acetate or the acetic acid? Why would it be the acetic acid? Right? I can't have two bases on the same side. That doesn't work out. So it has to be the acetic acid. All right, so if I know I have acetic acid and I have hydroxide, what will be one of the products? All right, we know we make water. Then what must the other one be? Right, the sodium acetate or just the acetate.
So it's okay if you write it with like the sodium here, right?
You can, just don't let them confuse. So like the sodiums are going to be on both sides in this case because they have sodium hydroxide and sodium acetate. They have a cancel, so it is not inappropriate to write them. I just leave them off because I don't care how many moles of sodium are in there. All right, so ready? We're going to write a new type of ice chart. Hopefully everybody's ready for the excitement this is. All right. So we're going to start off again with initial. In my original solution that we found in part 1, was there any hydroxide in there? Right, it said I had a solution of acetate and acetic acid. So is there anything that has? No. All right, and then we found moles of acetic acid initially, and that was what? I have no idea where I wrote that. Oh, there it is on the other page. 0.375. And obviously that's water, and that doesn't matter. And we found this to be, there we go. Here's our new line. Hopefully everybody's excited. It doesn't make anything cool. IACE. Before it was an ice chart, now it's a IACE chart. So in this situation, I didn't have any hydroxide initially, but I added hydroxide. So the hydroxide I added is this moles, 0.0021. And I didn't add anything else, so those are still zeros. Okay, looking at what I added compared to the other reactant, which one will be used up first, the hydroxide or the acetic acid? Hydroxide. So I need to subtract the hydroxide from both reactants and then add it to the products. Is the limiting reagent. And it gets used up first. All right, what am I left with? What's the relationship between these two? Right, they're conjugate acid bases. And I want to find the pH, so what equation do I need to use? Henderson has a, okay. So I've added base to my original buffer. Do you expect the pH has become more basic or more acidic? It should have come more basic, so do the math and make sure it is. We were at 4.94. We should be a number closer to 5 probably at this point. And that intuitively makes sense, right? We added some base, which means the base concentration's gone up, which means our pH should be closer to 5 compared to where we were. Good. Okay, how are we feeling about this? We'll use your thermometers. Awesome. Let's do some more problems. I have no idea what's going on in this class. Okay, mostly up, some middles. Okay, if your thumb is currently down, come and see me. I have millions more problems we can work through. I'm going to stop class for today because there's not enough time to like really start another problem. But we will do some more buffer problems Friday and then move on to the next section, which is titrations. Yay! We're going to do titrations and do titration curves. Be able to sketch graphs. Yay, graphs. And then we'll work on solubility rules. This is just the best chapter all around. It's like just all kinds of great math. So, into the quiz on Friday, we'll cover up through these kinds of base problems, acid-base buffers. So, up through what we just covered